Welcome to Homework Lib.
This is chapter 35, problem number 26. We have an air wedge, basically put in between glass. This is glass, here is glass, and here between is air, the angle theta. So let's look at the overall phase shift to determine what equation to use for the constructive interference for the bright fringes. So at this interface, when the light strikes the interface, there is actually no phase shift from the upper part because the light is going from a higher index of refraction towards lower, so there is no phase change upon the reflection here. But in this boundary, it's not the same, right? There is an overall 180 degree phase change. So the overall phase change is 180 degrees from the two interfaces that we have. So then for the constructive interference to happen, we need to have at least the thickness 2t equals m1/2 lambda, right? So then let's look at, so what we're trying to get from here is basically the distance between the two fringes, and then we can find the density of the fringes, right? So we're trying to get to x. So let's pick an arbitrary point. Here, let's call this the thickness t based on the x on the glass. Then our angle tangent theta would be equal to t over x, right? So then t, the thickness would be x tangent theta. Now let's plug this in the first equation that we wrote so that we can write everything in terms of x, because that's what we're after. 2x tangent theta is going to be m plus 1/2 lambda. Then x from here is m plus 1/2 lambda over 2 tangent theta. Now, if you write it as a function, xm then as a function of m is going to be m plus 1/2 lambda over 2 tangent theta. And the fringe, the position of the fringe right next to the initial fringe, then m plus 1, we can write it as m plus 1 plus 1/2. We can formulate it this way, right? 2 tangent theta. Then delta x between the two would be m plus 1 minus xm, so that we have m plus 3 over 2. I just added 1 to 1/2. It will be lambda over 2 tangent theta minus m plus 1/2 lambda over 2 tangent theta. So then lambda over 2 tangent, let's go to the next page from here. Then delta x would be lambda over 2 tangent theta, m plus 3 over 2 minus m minus 1/2. And they're going to cancel, and this gives us 1. So delta x is going to be lambda over 2 tangent theta. Now what we're after is actually the number of fringes per centimeter. So what we're looking after is actually the inverse of this, 1 over delta x. Either find the answer here and then take the inverse, or just from the beginning, just take the inverse of 1 over delta x. So I just want to mention one thing. What's given in the problem is actually tangent theta is given in the problem in terms of the thickness. So at the end of the wedge, so here there's a metallic part that is actually given to us in order to calculate that. We can say, well, the thickness of the metal divided by the overall length of glass, right? So let's say thickness of metal divided by overall length of glass, L, let's call it. We can actually plug this back in here. So what we can do is we're inversing it to tangent theta over lambda. So 2 over lambda tangent theta is going to be T metal over L. From there, 2 T metal is given to us as 0.08 millimeters. So we're converting it to meters. Divided by lambda is 656 nanometers. So we converted it to meters as well. L, the length would be 9 times 10 to the power -2 meters. So overall, we find out that we have 2,710 fringes per meter, or we can say 27.1 fringes per centimeter.